Now let's talk about how pressure changes as we go down deeper into a fluid. You probably have some experience with this already. You know that if you dive down to the bottom of a pool, the pressure increases, and you may know that if you're here near sea level, the pressure is higher than if you go up at the top of some mountains. So let's try to understand that. Let's look at a slice of the fluid as if it were a solid particle. It's called talking about a parcel of the fluid. Now it's got sideways forces pushing out. Well, it's pushing out on its container and its container is pushing in on it. But if we focus on the vertical forces, it's very much like the vertical forces we would have on a solid object. We have a force pushing up from the pressure below. We have a force pushing down from the pressure above. And we have gravity. Now that should equal ma, but of course we're in static equilibrium, so the acceleration is 0. Alright, that tells us that the force up minus the force down equals mg. Well, I'm going to write this mass in terms of the density times the volume. I'm going to write these forces in terms of pressure times area. So this becomes the pressure on the top, that's the pressure on the bottom, times the area, minus the pressure on the top, times the area, equals the mass, which is going to be density, times the volume, which will be area, times dy, times g. Well, notice each one of these has the same area in it, so that cancels. And what I'm left with over here is just the change in pressure as we go down. So rewriting that, I find that dp dy is equal to rho g. Now, if the density is constant, that integrates very simply to say that the density is equal to the density at some reference point, usually atmospheric pressure at the top surface, plus density times gravity times the depth, how far down you've gone. Your book likes to write this with a minus here and calling h delta y. In this case, because h is measured down, it's a negative delta y, which cancels out this negative sign here. We get higher pressure the deeper into something we go. Now, in the case of atmospheric pressures, the density is not necessarily constant. In fact, the density is proportional to the pressure. We'll find out next semester that it's equal to the pressure times the mass of a mole of that gas, the molar mass, divided by the gas constant times the temperature. For our purposes, all we really need to know is that all of these things here are constant, and this is the pressure. So the rate of change of pressure with y is negative density times gravity, where plugging in the density, we get all these constants times the pressure. Then I can integrate that. All of those are constant. Integrate dy. Oh, you know what? It doesn't work quite like that. But this differential equation can be solved. We can't just integrate it dy because I need to put the pressure over here. What happens is we put the pressure on the other side. So we get dp over p equals negative mg over rt dy. And now we can integrate this. This part gives me the negative mg over rty. This part is log p over p naught, and when I exponentiate, I get this solution. I can also show that this solution works by simply plugging it back in there. So we find that pressure drops exponentially as we go up through an atmosphere that's at constant temperature. So we can use that if suppose we're driving along one day and we have a barometer to measure the air pressure around us. we might get a reading like this on our air pressure as a function of time. And we can then use that to figure out our altitude. These high air pressures suggest that we're relatively low in the atmosphere, relatively low altitude, whereas these very low pressures suggest we're going over some kind of mountain peaks. And in fact, this data was taken by a man driving along a mountainous road and going over two local peaks.